Hi students, welcome to HSC Chemistry and the production of materials topic. In this video we're going to be comparing different polymers. Now this is a big one, and what I suggest you do is to draw up a table like this one, a comparison table with the four main types of polymers that you need to consider. That's low density polyethylene, high density polyethylene, PVC or polyvinyl chloride, and polystyrene. And I'm just going to very quickly work through the slides in this presentation. There's quite a lot of them, but I'll try and work through them relatively quickly so that we just get a general picture. What I suggest you do is to jot down the main properties and the uses for each of these different polymers so you have a good comparison table for them. So here's a little exaggerated picture of LDPE, lots of branched chains and repeating units. Because of this, no chain stiffening and no cross linkage means that LDPE is very highly flexible, but it has a low melting point and low mechanical strength. And this makes it useful for disposable shopping bags, cling wrap, those soft milk bottles and squeeze bottles. So the ones that don't have a rigid shape, more those really soft, soft types of plastics. So you can see them here, plastic shopping bags. All these little bottles that are quite squeezy and soft, they're LDPE. HDPE is long chains, much more densely packed, tighter structures, and as a consequence of that, low degree of branching, tightly packed chains, and that means that we have low flexibility, a high melting point, and mechanical strength. So these are more rigid and strong, rather than the flexible ones that we saw for the LDPE. And so as a result, things like kitchen utensils or wheelie bins, lunch boxes are the sorts of things that you find made out of high density polyethylene, these sorts of things, okay? Handles of knives and these sorts of plastics tend to be more of the high density polyethylene type, and I'm sure we're all familiar with wheelie bins. PVC is the third one, and this is where one of the hydrogens has been replaced with a chlorine. So you can see that's the structural change to the monomer, and the monomer is vinyl chloride or chloroethene. And so then we polymerize it in exactly the same way. It's just obviously we have alternate repeating units. If you put carbons, several carbons along, then you're going to have hydrogens alternating with a chlorine, and so on. Now PVC, you can see here the bond opening. The polyvinyl chloride is just alternating chlorines every second one along, just to show how that structure occurs. Here's a sort of oversimplified diagram where the green little balls represent the chlorine atoms. And for pure PVC, we have a very hard, inflexible plastic with limited uses. And one of the reasons for that is the large number of chlorine groups within each of those long chain molecules. Because the problem is we have polar bonding, and therefore we have dipole-dipole interactions, and these are much stronger intermolecular forces than dispersion forces. And because of that, there are very strong forces within the PVC polymer, and that makes it harder, but it also means that there's no flexibility. The presence of the Cl is also what contributes to chain stiffening, and that's what creates this inflexibility, high melting point, and high strength. Things that are made out of PVC include piping, electrical and water pipes, because obviously it's inert, it's not going to dissolve in water or anything like that. Credit cards, another thing you may not be aware of that can be made from PVC, and the water pipes that we see on our homes. Flexible PVC only becomes flexible with the addition of certain types of additives, and so garden hoses and electrical wiring are important sources. Particularly in terms of electrical wiring, the problem that we have is if the coating burns, then hydrogen chloride can be evolved. And this is hydrogen chloride gas, not to be confused with hydrochloric acid, which is what happens when this gas dissolves in water. So this, in the gaseous form, is a fire retardant, And that's one of the reasons why it's useful for wiring, but it's also one of the reasons why with these sorts of electrical fires, we don't want to be using water to put them out. And the fourth one we want to look at is polystyrene. Now, polystyrene comes from the monomer styrene, which is ethynyl benzene. In this case, we talk about the benzene as being the main structure, even though we've confined ourselves very much to derivatives of ethene. And you can still see here's the original ethene, hence the ethynyl, but it's attached to this benzene ring, which is what gives us the styrene. And when you put lots of them together, you get polystyrene. Now you can see the presence of these ring structures scattered throughout the long polymer chain, and of course this creates additional problems. And here's the structure of the benzene ring here, and there is the double bond in the original ethene. So again, our double bond opens and the polymerization occurs with the benzene rings occurring every second carbon along the chain. What this does is produces a polymer that has a couple of different types of properties depending on how it's treated. Most of the time when we think of polystyrene, we think of the polystyrene balls or beads or cups. That's probably the best known, but it's probably not the most common use in your home. And you'll see that in just a moment, mainly because the presence of this big benzene ring leads to a very high degree of stiffening of the plastics, and that means it's very inflexible and very brittle, and it's relatively easy to damage. There's very little to no chain branching. Of course, those big benzene rings are going to get in the way of any sort of chain branching occurring, and so as a result of that, it's very straight chains. They're not densely packed, of course, because those big benzene rings also limit the amount of dense packing that can occur as well. But the regularity of the structure actually leads to this property of transparency. And this is an interesting one because it is going to be a polymer with low density, transparency, and brittle nature. And that is very commonly found in DVDs, CD cases, Blu-ray cases, and so on. These are probably not the things that you first think of when you think of polystyrene, and yet this transparent, brittle, easily cracked kind of plastic is what's characteristic of polystyrene. But of course, if you blow air through the polystyrene, you get a different type of polymer, and that's how we get our cups and our beanbag beans and things like that. So before the polystyrenes actually had time to cool, in the liquid form, we blow a bit of air into it, we get a completely different type of polymer that is now no longer transparent. It's much softer, it's even higher density because of all of that space, so that makes it very lightweight. It's also a very poor conductor of heat, which is exactly what you want for your cups that are going to hold your hot drinks. And so here's again some examples of this sort of foam packaging, the little bean bags that we see, and of course these cups are all examples of polystyrene. Just a couple of quick final notes there, and I can see the time's marching on, but let's just finish it off here with a couple of environmental thoughts. The one thing is that all of these polymers that we've looked at are all derived from ethene, and ethene itself is derived from crude oil. And so what we're doing each time we produce these plastics is we're using up a valuable non-renewable resource. All of these plastics we've looked at are not biodegradable. Bacteria and fungi can't break them down, and they stay in the environment for a very long time. If we throw them away, they stay as landfill for long periods of time. Worse than that, a lot of them are ending up in the oceans, and that's interfering with wildlife. And I'm sure you've seen plenty of videos of different types of animals and birds with caught in plastics. In our own landfill, about 20% is made up of plastics. And as I mentioned, animals can sometimes mistake them for food or just get caught in them, and they can have major issues. So here's a little description of some of the different types of ones. The HDPE, the LDPE, the vinyl chloride, and the polystyrene are the ones we've looked at most specifically. You will find polyethylene terephthalate, which is the PET bottles. They're very common as well. And also polypropylene. These ones occur around the place as well. But these are the ones that are of most importance for your course and that you're expected to be able to talk about in some detail. In order to really effectively recycle, we actually need to separate all of these plastics out from one another, and that is time consuming, and it also increases costs. And so one of the ways to try and do that is to have a labeling system that helps to group these together more effectively. At this point in time, of course, it's still a little bit more expensive to recycle than it is to make new plastics, which is why they continue to be produced. We can burn them. Sometimes the waste gases can be quite toxic, and because they're basically made of carbon and hydrogen, carbon dioxide is going to be produced if it's incomplete combustion, and we're also going to get carbon or carbon monoxide being produced as well. And so what we're looking for is a solution that's actually going to be able to replace some of these plastics, and that's the area of biodegradable plastics or biopolymers. But we'll have a look at that in one of the upcoming videos. Thanks for watching.